Lesson: Deep Learning Theories. Deep learning, a subset of machine learning, has emerged as a powerful tool in artificial intelligence. Characterized by its use of artificial neural networks with many layers, deep learning has revolutionized numerous fields, including cybersecurity. Understanding deep learning theories is crucial for grasping the theoretical foundations of AI, particularly in enhancing cybersecurity measures. At the heart of deep learning lie artificial neural networks, which mimic the human brain's structure and function. These networks consist of interconnected nodes or neurons, organized into layers: an input layer, hidden layers, and an output layer. Each neuron processes input data and passes the output to the next layer, allowing the network to learn complex patterns. The fundamental theory behind deep learning involves gradient-based optimization, specifically backpropagation, which adjusts the weights of the connections between neurons to minimize the error in predictions. This process is repeated iteratively to improve the model's accuracy. Deep learning's theoretical foundation also includes understanding activation functions, which introduce nonlinearity into the network, enabling it to learn more complex patterns. Common activation functions include the sigmoid, hyperbolic tangent, and rectified linear unit. Each function has its strengths and weaknesses. For instance, ReLU is widely used due to its efficiency in reducing the likelihood of the vanishing gradient problem, which can hinder the training of deep networks. Another critical theory in deep learning is the concept of overfitting and underfitting. Overfitting occurs when a model learns the noise in the training data instead of the actual pattern, leading to poor generalization to new data. Underfitting happens when a model is too simple to capture the underlying structure of the data. Techniques such as regularization, dropout, and data augmentation are employed to mitigate these issues. Regularization adds a penalty term to the loss function to prevent overfitting, while dropout randomly drops neurons during training to reduce reliance on specific neurons, promoting a more robust model. Deep learning models often require vast amounts of data and computational power. The theory of transfer learning addresses this challenge by allowing a model trained on one task to be repurposed for another, reducing the need for extensive training data and computational resources. This is particularly useful in cybersecurity, where labeled data can be scarce. For example, a deep learning model trained on general network traffic can be fine-tuned to detect specific types of cyber threats, enhancing its effectiveness and efficiency. In the context of cybersecurity, deep learning theories are applied to various tasks, such as intrusion detection, malware classification, and anomaly detection. Intrusion detection systems benefit from deep learning's ability to identify complex patterns in network traffic that traditional methods might miss. For instance, recurrent neural networks and their variant, long short-term memory networks, are effective in analyzing sequential data, making them suitable for detecting anomalies in network traffic over time. Malware classification is another area where deep learning excels. Convolutional neural networks, originally designed for image recognition, have been adapted to classify malware by treating binary files as images. This approach leverages CNN's ability to capture spatial hierarchies, enabling the identification of malware based on the structure of the binary code. Research has shown that CNN-based models can achieve high accuracy in malware detection, surpassing traditional machine learning methods. Anomaly detection in cybersecurity involves identifying deviations from normal behavior, which may indicate a security breach. Autoencoders, a type of unsupervised neural network, are particularly effective for this task. They learn a compressed representation of the input data and attempt to reconstruct it. Significant reconstruction errors can signal anomalies. Autoencoders have been successfully applied to detect anomalous activities in various cybersecurity domains, providing a robust tool for identifying potential threats. Despite their advantages, deep learning models are not without limitations. One significant challenge is their interpretability. Unlike traditional machine learning models, deep learning models are often considered black boxes due to their complexity. This lack of transparency can be problematic in cybersecurity, where understanding the reasoning behind a model's decision is crucial for trust and accountability. Efforts are ongoing to develop methods for interpreting deep learning models, such as feature importance analysis and visualization techniques, to make them more transparent and trustworthy. Another limitation is the susceptibility of deep learning models to adversarial attacks. These attacks involve subtly altering input data to mislead the model into making incorrect predictions. In cybersecurity, adversarial attacks can be particularly dangerous, as they can bypass detection systems by exploiting their vulnerabilities. Research is focused on developing robust models and defense mechanisms to mitigate the impact of adversarial attacks, ensuring the reliability and security of deep learning-based systems. In conclusion, deep learning theories provide a robust framework for developing advanced AI systems capable of addressing complex cybersecurity challenges. From the structure and function of artificial neural networks to the techniques for mitigating overfitting and underfitting, these theories underpin the development of effective deep learning models. Transfer learning, recurrent neural networks, convolutional neural networks, and autoencoders are just a few examples of deep learning applications that enhance cybersecurity measures. However, challenges such as interpretability and adversarial attacks must be addressed to fully realize the potential of deep learning in cybersecurity. By understanding and applying these fundamental theories, we can develop more sophisticated and resilient AI systems to safeguard against evolving cyber threats.